Thank you very much. First time I've used this, so it's a natural paranoia, I'm afraid. Okay, so I'm going to talk about what Scott called hero calculations, but sort of more generally trying to look at how our applications currently scale and where we want to be going. Okay, so okay, that's how it works. So how do you scale out to these 750,000 cores that Archer 2 is going to give us? And as Simon said, beyond that, well, one obvious way, which Tom is going to talk about, is lots of loosely coupled calculations. And now for systems of the sizes, computational systems, I should say, of the sizes we're talking about, we could be looking at hundreds to thousands of these things. So actually keeping them under control is a major piece of effort just in itself. But what I'm really going to concentrate on is if we have one large calculation we want to do, where do we stand with scaling that out to, well, on Archer, let alone Archer 2, and how are we going to do it? Now, there are a number of issues. You know, our applications must scale out to the process counts we require, and we must use the hardware effectively. What I'm not going to touch on is I/O, and I think in many ways I/O is actually the most difficult issue, so I'm going to leave it to somebody else because I don't know how to answer that one. So, okay, so how do we perform at the moment? Well, the honest truth is, in a lot of our applications, not as well as we might hope. I'm going to have a quick look at a few examples and just point out one or two fundamental problems that we have. And if we really are going to scale out these big calculations to many cores, more than we currently do, what kind of things we have to overcome, and do that very quickly. But to get a real proper picture of this, we have to do some proper benchmarking and profiling, and Andy's breakout group is going to address that particular one. So what I'm going to have a quick look is classical MD, plane wave DFT, and local basis set electronic structure calculations, kind of meat of drink of what we do in the materials modeling type thing, and make one or two observations. So let's have a look at scaling of a couple of codes of classical MD, just modeling. Common salt comes out of your dispenser in your kitchen, stick it in your pasta or whatever you want. Okay, so I'm looking at a fairly chunky system, 1.7 million atoms of sodium chloride, and I'm running it with both lamps and DL Poly. It runs on Archer 4. DL Poly 4 runs on Archer. Okay, so on the left-hand side, I show the speed up for the calculation. You can see two sets of lines really. You can see the top set of lines running at roughly 45 degrees to the axis, and these are scaling near to perfectly. On about 3,000 cores, I'm getting about 3,000 speed up, and that's wonderful. And this is actually the speed up the short-range force evaluation of the code. This bit parallelizes wonderfully, and both DL Poly, DLP short, and LAMP LMP short in the legend show how well those are scaling. On the other hand, you've got another set of lines further down, which is the long-range contribution to the AVALT. Okay, and if we look at the right-hand curve, you can see how this, as the process count starts to increase, how this seems to dominate. Well, it doesn't seem, it does dominate the DL Poly calculation. It goes over from 40% to over 50%, and while the DL Poly short-range calculation is decreasing. And this dominates the scaling of DL Poly. The DL Poly total scaling, the scaling of the whole runtime, is the red line. Okay, you can see that it's way below the perfect scaling of 3,000. And that's purely because of this long-range force evaluation. And this is ultimately because we use a fast Fourier transform. I'm afraid that fast Fourier transforms, for fundamental reasons, cannot and will not ever scale well to many processes. And I think this is something we have to start facing up to. There are a number of algorithms that we've used over the past, really good science. I'm not criticizing science at all. I'm just saying that if we want to scale further out, we have to start thinking, are these the algorithms, the hardware that we're looking at the moment, and what we have to replace them with? Now, if we're talking fast Fourier transforms, of course, why don't we look at plane wave DFT? So thanks to Phil Hasnett for providing some numbers over the weekend, and this is a CAS-step calculation. You know, a few hundred atoms of alumina, the kind of thing that people might want to be doing as part of their standard calculation day to day. How is this scaling on Archer? And we can see that if we look at the total speed up on the right hand side, we're getting about 400, maybe 500 speed up on 2,000 cores on a good day. Okay, and this is purely dominated again by the FFTs. As I said, the point I wanted to make is FFTs fundamentally can't scale, and we have to think what we're going to do about it. Now, it's not all bad news for plane wave DFT. The speed up of the total is a lot better than the speed up of the FFT itself, because we have two K points, and parallelism over K points is essentially perfect. And if there are other forms of hierarchical parallelism we can find within these calculations, we can scale out to somewhat more processes. But if we have to do an FFT of the whole of the machine or large proportions of the machine, we're going to get hit by scaling issues. Let's have a quick look at local basis set calculations. This is Crystal, the code that I spend probably the majority of my time working on. And you can see here that this is a calculation for MCM41. It's a fairly chunky calculation. It's a little over 9,000 atoms with 120,000 basis functions. This is actually a 16 by supercell of this zeolite. And we can see in this particular calculation again, part of it, the integrals, is scaling pretty well. We're getting over 12,000 speed up on 16,000 cores, which is not too bad. But the speed up of the whole code, the purple line in this case, is being degraded by the parallelism within the linear algebra. We're using a ScaleAPAC for this, and this is totally dominated by diagonalization. And again, because like FFTs, diagonalization requires communication between a very large number of the cores within it to keep your eigenvectors orthogonal, this again is something which is very difficult to scale out to many, many cores. And again, if we're going to think about using diagonalization in the future, we're going to have to find either further levels of the hierarchy or think about how we're going to move away from diagonalization if we're going to use these 750,000 cores on Archer 2. Okay, so I keep forgetting how to do this. The point I'm trying to make here really is that the assumptions that we've made about how to do algorithms when we get out to 750,000 cores might not be what we've used in the past. An FFT is fast, that's what the F stands for, but not necessarily on a distributed memory machine. Your floating point operations are quick, but you spend your whole time doing communications, which degrades the performance and eventually kills you. Similarly, in quantum chemistry calculations, the assumptions over the years has been the integrals dominate. If you look at the last slide I just showed, it's actually diagonalization was taking 90% of the time. We have to have a little bit of a rethink, in fact a major rethink, about where we're going and how we implement solutions to our problems if we want to get up to 750,000 cores for hero type calculations. Okay. Basically, anything that uses the whole of the machine, anything that does communications across the whole of the machine is going to cause problems. You might want to compare this with halo exchange type algorithms. We've seen an example of this actually already, how the short range forces are done in DL Poly is essentially a halo exchange algorithm. These scale very, very nicely indeed, because basically you only ever communicate to a set number of processes in 3D, essentially 27 normally maximum, sorry, 26 normally maximum. Okay, whereas if you might be scaling, it might be communicating to the whole machine if you're doing an FFT. Halo exchange scales very nicely, FFTs don't. The fundamental reason is that you don't have to increase your communication cost per core process as you actually scale out the problem. So we have to have a little bit further to think. There's some wonderful papers that have done really good science, will continue to do really good science over the years in the future on medium-sized systems. But these, if you look at the dates, were written before parallel computing became the modus operandi of HPC in computational science. I've given some dates there. The Cray T3D, which is possibly our first big parallel machine in the UK, came in 1993, and most of the papers which were basing our algorithms are about the same date as that or beforehand. So maybe it's time for a think again. Okay, so we have to start thinking about solution methods which don't just solve efficiently and accurately our problems, but also map well onto the hardware that we're trying to provide them with. And these are big parallel machines if we're going to scale out. Talking of hardware, we have more elephants in the room, in particular accelerators. I don't want to go into this, partially because I'm not an expert on accelerators. Simon has mentioned them, and it's not entirely clear what they will be. GPUs being probably the favourite at the moment, but we have to keep that in mind. How are we going to use them? How are we going to keep our maintenance costs for software on them? How are we going to program them? I think these are all open questions and things that should be discussed in breakout groups today and in the future. And I'll leave it at that. The other thing, as Scott indicated, just to bring up, is we really need to identify what kinds of problems we're going to solve. I've given one or two indications of talking with some of my collaborators, especially in the Crystal project, what they might do if I gave them. I gave them the question, I'm going to give you a 200,000 core machine which Crystal scales perfectly on, what will you solve? And these are one or two ideas. But I might also just point out, if we have more scalable solutions, this also will help this problem size that we're currently doing at the moment. Because instead of getting 1,000 speed up on 3,000 cores, we might get 2,500 speed up on 3,000 cores and appreciably better throughput on those kinds of problems. So it's not just the hero problems that our scaling improvements will help. It's trickled down to the more moderate size and medium size, the kinds of things we're doing today will be aided by better scaling codes. So in summary, with the possible extension of quantum Monte Carlo, which must be mentioned, we are actually struggling to scale to current process counts. We need to put effort in to address that if we're going to scale out to the much bigger system sizes. Don't really want to say too much more, apart from one thing I really should have mentioned in the wave past on the previous slide. What might we do? It's not just bigger systems. One thing we should also start thinking about is, do we want to consider current size systems with more accurate methods of solution? So for instance, if you look at the American proposals, while there's not an awful lot on density functional theory, there's huge amounts on coupled cluster and highly accurate wave function methods. Is this a direction we want to be going? But anyway, that's where I'm going to go. That's where I'm going to call it today. We really need to, in my opinion, we need to start thinking about what our basic fundamental algorithms are. We need to bring in the mathematicians and the computational scientists if we want to scale out to these larger system sizes. I think that's it. Okay.
Thank you, Ian.